we've just been looking at acceleration. We're now going to go back to motion graphs to look at velocity versus time, because again, acceleration is tied into that graph. As we saw with displacement versus time, the gradient of a displacement versus time graph gives us velocity. So naturally it follows that the gradient of a velocity versus time graph is acceleration. So in both cases we're looking at the change in a quantity over time. So change in displacement over time gives us velocity. The change in a velocity versus time graph gives us acceleration. And just a point of difference here to note as well. Previously we looked at average velocity and instantaneous velocity. We don't usually talk about average acceleration, so we wouldn't usually talk about, say, from t equals 0 to t equals 5, what was the average acceleration in that period of time. We usually are only interested in the instantaneous acceleration, so we won't worry about average acceleration here, but the calculation method would basically be the same. So to calculate acceleration from a velocity versus time graph, to calculate acceleration, in this case we'll use t equals 7 as an example. 7 seconds. So in that scenario, if we're looking for the acceleration when we're dealing with this point in time here, then we can look at the gradient of that slope section, and so we use sort of the extremes of that, so look at t equals 6 to t equals 8, and so the calculation would be as follows. So the acceleration is going to be equal to the change in the velocity over the change in time, and the change in velocity there, we finish off at 0 meters per second, and we subtract from that -1 meters per second, and divide that by 8 seconds minus 6 seconds, which gives us a value of 1 over 2, or in writing as a measurement, 0.5 meters per second squared. And notice that the value there is positive, so we should identify that that's 0.5 meters per second squared in the forwards direction. Now this idea of forwards and backwards is an important one to consider here, so let's just go back to the graph. I want to just draw your attention to a few things here. So we've got that this here is accelerating forwards, so in that region we'd say that it's accelerating forwards, but notice that the velocity is negative. So it's accelerating forwards, but it's actually moving in reverse. Notice too there that the speed is decreasing. So while it's accelerating forwards but moving in reverse, we could actually say here that it's decelerating because its speed is decreasing. If you look at this part here, which is going to be similar to the part at the top, so this region here, we would say that there's no acceleration. So we can see that because the gradient would be 0. Another way of saying no acceleration is saying constant velocity. So that, as I said, would apply up the top as well. So we could just put combine both of those. Now we'll go to this point over here next. It's the easiest one to look at. We would say here that it's just accelerating. So it's accelerating, it's moving forwards, the speed's increasing, velocity is increasing. This one here I want to break up into two regions. So above the line, we would say that the object here is decelerating because its speed's decreasing. But in this case, it's still moving forwards. So notice that its speed is decreasing, its velocity is decreasing, but it's still actually moving forwards. We would then be interested in the next point that's particularly worthy of note, is this one here, is where the object would momentarily be stationary. So for a brief instant in time, it comes to a stop. And finally, the last one to consider is this little section underneath. Here we would probably look at this as actually being an acceleration rather than a deceleration now, because it's come to a stop. It's accelerating, but it's accelerating in the reverse direction. So its speed is increasing, the magnitude of the velocity is increasing. So accelerating in the reverse direction, and then that leads into where we started, accelerating in the forwards direction, but it's still moving in reverse, and so we would call that decelerating. So note here that there's you need to consider what the motion of the object is, whether it's moving forwards, backwards, and then consider its acceleration as well. So just because it's a positive acceleration doesn't always mean that it's speeding up. It can actually mean that the speed is decreasing, as we see at the end here, where it comes back to zero. I can also just point there that that's momentarily stationary too. So there's some ways to interpret, or things to keep in mind when you're interpreting a velocity versus time graph. Now there's another useful aspect about velocity versus time graphs that I want to discuss in a bit of detail here as well. That aspect is sort of related to geometry, I suppose, and that aspect is about the area under the curve. That term, area under the curve, it's something to that you'll become familiar with, hopefully. It's a mathematical thing more than anything, and what it basically means is the area that's bounded by the line that you've graphed and the axis, the horizontal axis. So when we say area under the curve, we really mean anywhere between a line that's been graphed and the horizontal axis. So if you think about this scenario, when you talk about area, we're really going to be multiplying two quantities together, and the area that we're dealing with is the product of velocity and time. So by that I mean that if you look at the two axes, you've got velocity on the vertical axis, you've got time on the horizontal axis. So to calculate the area, you're multiplying those two together. If we go back a step and have a look at the definition of velocity, we looked at the fact that velocity was equal to the change in displacement over time. If we rearrange that, we could then say that the change in displacement, sorry, there should be change in time there, change in displacement is equal to the velocity multiplied by the time. So to link those two things together, the area that we're calculating is velocity by time. This equation here, we've shown that velocity by time is equal to the change in the displacement. So that means that the area under the curve is displacement. Now to explain that in a little bit more detail, let's go back to the graph and we'll pick a time. Let's say we're looking at what happened, the displacement after 3 seconds. So we're looking at the area that's bounded by the graph, the horizontal axis, and a time of 3 seconds. So that's the area that we're going to be looking at there. Now all we need to do here is just a little bit of geometry. We'll actually break this up into two regions. It'll probably be the easiest way to do it. So we've got a rectangle there, and then we've got a triangle here at the beginning. So from 0 to 2 seconds, the velocity increases to 2 seconds, and then from 2 to 3 it stays constant at 2 seconds. So we can figure out those two areas, add them together to calculate the displacement. So if we do that, so for example, from t equals 0 seconds to t equals 3 seconds, we would say that the change in displacement, I'm just going to do the calculations there. The first section was a triangle that had a base of 2 seconds and a height of 2 meters per second, and the second section was a rectangle that had a base of 1 second and a height of 2 meters per second, And if we add those together, we would get that the answer there is 4 meters. Again, notice that that's a positive, and so that would mean that it's 4 meters forwards. So there's a quick example. We'll do a few more of those sorts of calculations in class, just to get you familiar with looking at that area under the curve idea. One last thing, just going back to the graph again, you'll notice that we have this area above the curve, so I would say that that's positive. If we calculate the area below the curve down here, we'll actually be using a negative velocity over on this on the axis on the side here. Now usually we wouldn't consider area to be negative. Here we can, because it's not actually area as such, it's displacement. So the area can actually have a negative value. So above the axis, the area is positive. And again, when we say area, we're not really talking an area. What we're really saying is that it corresponds to a positive displacement, and in this case positive means in the forwards direction. Taking that a step further, area below the axis would be negative, and that would mean that part of the displacement is in the reverse direction. Now, if we were looking from, say, t equals 0 to t equals 8, we've got two regions, t equals 0 seconds to t equals 8 seconds. We've got two regions that we would need to calculate the areas for. The area above is slightly bigger, so it has a larger value, or has a larger magnitude. So we can simply add the two together, so the positive area above, and as a result that means that we're going to end up with a positive answer. So the final displacement at t equals 8 seconds will still be forwards. So that's a way that we can figure out the location of the object just using the velocity versus time graph. We'll have a look at a few more of those sorts of questions in class, and do a few of those problems to calculate displacements, and have a look at some varying scenarios about where an object would be located based on its velocity versus time graph.